it feels like everything today is AI. Artificial intelligence that, large language models, ChatGPT. It's just like unending. And yet I think people are having a hard time finding really practical uses on a day-to-day basis for how they can actually take advantage of this technology. And I mean, there's so many artificial intelligence recipes that a person needs, or cat memes. But I think that the real promise of this technology is in science. You can take sciences that generate enormous amounts of data, you can feed them into this transformer architecture, and then you can start to make predictions that will be useful to scientists. And we're really at the nascent stages of this. Everybody's too busy building chatbots and not busy enough creating science bots. And hopefully that will change. So my guest today is Dr. Michael Smith. He's a researcher at Aspia Space and Universe TBD, and he is heading up the AstroPT and EarthPT projects. And these are exactly what I said, that you are taking enormous amounts of climate data, Earth data, astronomy data, and you are feeding them into a transformer architecture, and you are then generating next tokens, but the next tokens are things like the weather or galaxies. And it's sort of a really interesting, fascinating project. And they need help. They need more people to get involved, especially people who are programmers. So enjoy this fascinating interview with Dr. Michael Smith. Michael, we're all pretty familiar at this point with the promises of ChatGPT, large language models that can produce text like fancy autocomplete or can create images. But as an astronomer, as a scientist, how do you look at the technology of these large language models or like the transformer architecture and think about what kinds of possibilities are out there for science?
So I think the exciting thing for me is finding a nice way to compress all of the data out there. So you can see this with LLMs, where they're managing to compress text in a useful way for people. With the autoregressive architecture for science, we can do something similar by getting a load of scientific information, feeding it into a similar architecture to the LLM, and then compressing it in that way, and then using that compressed embedding space to do science progress on that. So that's the thing that excites me most, taking similar architectures that have been proven in the textual domain and then applying them in a similar but like adjacent way for scientific use cases.
But like, the experience that we've all had using, say, ChatGPT, where we ask it to write us a poem about, I don't know, your morning commute to work or whatever. And we know that it's been fed on just an enormous amount of data from the internet and then has been run through this transformer architecture that then makes this predictive next token model to be able to try and bring up the next text that it's likely to see. And somehow magically this creates poetry or whatever. It's not great, but at least it's doing it, which is kind of amazing. But so if the raw material for ChatGPT is the text on the internet, what is the raw material for, like, say, an astronomy based large language model?
So it's I would say it can be anything astronomy based. So we've been playing around with the AstroPT model by feeding in galaxy observations taken straight from the telescope, taken straight from the Dark Energy Survey telescope. And you just take the data from this, you put it in, you try and predict the next token or patch in a series of patches. And the model learns some underlying physical properties from this. But we don't have to stop at galaxies. We can feed in time series of stellar events. So if you have a strange stellar object that's doing a strange time series of brightness over time, you can feed this into the model as well. And it will learn something fundamental about how the star is performing, because it needs to learn is to predict the next token in the time series. So any observation that would be difficult to predict is useful to feed into a model like this, because in predicting this next step, it's learning something fundamental about the physics behind the scenes, which I find very cool.
I know there's been sort of similar work done in weather modeling, where
Hmm.
the traditional method is you'd have to come up with these enormous, very complicated supercomputers that would read in all of the butterfly wings flapping across various places and then try to predict the future rainfall in some other part of the world. And now they just like take a bunch of pictures of the world, and then the AI just predicts what the next frame is going to be, the next
Hmm.
token. If the tokens are pictures of planet Earth, then it knows how to predict future tokens, and it's much more energy efficient and so on. So let's go back to this idea then. So, you've got DESI, right, the Dark Energy Survey
Hmm.
instrument, and you've got millions of images of galaxies that have been taken. And so, what specifically are you doing to kind of prepare this data for AstroPT?
So that's the exciting thing. We don't have to do that much preparation. We can take the yeah,
Nice.
it's cool, right? You can just take the raw observations. You do a little bit of like quality cut, so you only take the good, like high quality, low noise galaxies, for example, or low noise time series or whatever, and then you can feed them straight into the model. And the model it can separate out the useful information from the not useful information without us having to do it manually. So we're cutting out a lot of the time consuming manual process here by feeding it straight into the model and asking it to sort out the problem. Um, yeah, and just to go back to your comment about the Earth observation uh, uh, climate models that you were just chatting about, we actually applied the AstroPT model, the large observation model, there to Earth observation uh, time series as well, and it works there too. So that's
Oh,
also
wow.
a publication, Earth PT we call it, and it's exactly the same model under the hoods, just on a
Yep.
different modality. So you can throw whatever at this model, and it figures
Huh.
it all out automatically, which is very neat.
Now, with
Yeah.
Earth, it makes sense because Earth goes through this cycle that that you're going to have weather patterns form and evolve, and they turn into other things around planet Earth and different features, and it is you're not going to get too far out of the norm, but with galaxies, like say you feed in 2 million galaxies into this system,
Hmm.
it's going to, how useful is it to predict the next galaxy?
It so this is something I found quite interesting in doing this work, and it was a little bit surprising to me. So in the paper, there's a figure, and it shows the loss per token fed, and it asymptotes towards a flat line at some point, and it's earlier than I would expect. And I think this is because galaxies are less information dense than Earth observation, for example. So in our Earth observation model, the line asymptoted lower, so it learnt more from the data set. But I think in astronomy, you can overcome this with the inherent multimodality of it. So if you have a galaxy observation in RGB band, GRZ, and you would also have a corresponding spectra, which is like a 1D description of the galaxy, you can feed this in together, and then you would get more information compared to just the GRZ bands. And you can also go away and get some other modalities too. And this would give the model more to learn physically about the universe. So it needs to do more. So the loss should continue decreasing as it learns there. So it should have more to learn. Yeah.
So, so you could give it, say, a million galaxies
Hmm.
and then spectroscopy pairs, and then you give it a galaxy that you don't know the spectroscopy data on it, and ask it to guess what it thinks is going to be the chemical signature, the absorption line, so on and so forth of that galaxy, and then find out whether or not it was how right it was.
Yeah, that's one scientific use case we're trying to get
Right,
started
right.
now. And there's also some upcoming work of a giant data set of all modalities of astronomy. Hopefully, will be out in the next couple of weeks or so. I can uh, I don't know, do something, show it, send it to you. But yeah, it's all
What's the so?
very exciting
But what's the
stuff.
gist?
Yeah,
But what's the gist of that? Like, what are you hoping to do, or are you under embargo still?
no, not under embargo. So it's
Okay, okay.
it's it's just a huge data set of galaxies, time series of stars, time series of any astronomy observations, galaxies from several different instruments, plus some tabular data too. And we're calling it multimodal universe. And yeah, it's just a huge data set. If you know Eleuther AI's pile from the textual domain, it's kind
Yep.
of like this, but for astronomy, it's going to be all out in the open so people can go and play with it. I'm very
Right.
excited about this. I think it should supercharge research into these large astronomy models.
So just to sort of explain this, you've gone into every available data source, pictures from DESI, from other telescopes, spectroscopy data, things from Gaia, everything you can get your hands on, normalized it, put it into one big database that can then be fed into various large language models that people want to try to come up with scientific uses of that.
Exactly the case, but not a
Okay.
large language model. You need to do some tokenization to make it work for a large language model, but a large observation model like EarthPT, you can feed it
Sure.
straight in. Yeah.
Like a transformer model.
Yeah, transformer model.
Like
Yeah,
a,
it'd be perfect. Yeah, it should just work.
right.
Yeah.
Okay. So, and so in the paper, the AstroPT, which people should definitely check out, you showed some examples. I saw like you had a grid of 15 out of 16 tiles of a galaxy, and then you had the software try to draw the last
Mhm.
piece. So how would that be useful scientifically?
So that's the surrogate task, and the reason behind it is just to give the model something to learn that's easy to define. So if we predict the next square in the time series, it needs to learn something about the underlying galaxy and the underlying physics to predict the next square. It's not so useful in itself scientifically, but once you train the model on this, you can take the embeddings in the transformer, like a intermediate layer, and then train a linear probe, which is just a linear regression, and try and predict some scientifically useful properties of the galaxy. So this could be the color or the magnitude in certain bands, or the redshift, how far away it is, or something like the morphology of the galaxy, which is also scientifically useful. And the exciting thing we found here is if you have a bigger model, it's better at predicting these downstream tasks, even though it's only trained on the next square in the time series, in the galaxy prediction. And this is something that we also see in large language modeling. So I found that very exciting to see this connection between large language modeling and this large transformer model. It's the same model under the hood, but it's a completely different modality.
Right.
Yeah,
I mean, we
yeah.
see these scaling laws. We see
Hmm.
how just more compute, better data, more time spent actually training the model, it starts to develop not only sort of performing the task that you expect, but is actually starting to come up with meta skills that underlie the task itself. So, so and I can think of other examples like JWST only has so much time to be able to image galaxies at really high resolution, but then you've got a better background of, say, coming from DESI or from Euclid, where you're going to get these galaxies, but they're going to look pretty crappy because it just doesn't have the same kind of capability as Webb. And so theoretically, you could match them up and say, here's the galaxy by Euclid, here's the one by Webb, here's the one by Euclid, here's the one by Webb. Okay, here's the one by Euclid. What would the Webb one look like? Zoom in and enhance.
Yeah. You can definitely do this. This is something I've been working on these past couple of weeks, just to uh, figure out a way so that we can match these pairs together, and then we can say maybe train a diffusion model on the tokens that it learns on the
Yeah.
matched pairs, and then diffuse into Webb or whichever you want, diffuse into Spectra if you like. So that would be very cool to implement this. It's on,
Wow.
yeah.
Diffuse into spectra or diffuse into Webb. So like Mid Journey or
Hmm.
whatever, or you ask ChatGPT to draw you a picture of, I don't know, whatever.
Yeah,
You would be getting, it would be diffusing an image that it would be predicting would be based on that underlying data.
yeah. I
And
think that,
obviously,
yeah.
people are going to say, well, it's probably just, it could be hallucinating. So where do you think the scientific, like, what is the scientific value if there's a potential that it's hallucinating? Then the error starts to creep in, right?
So I think the scientific value here is maybe to predict or to build a database of rare objects. So even if it's hallucinating, if you've only got one example of an object, say a green bean galaxy, and then you can diffuse 1,000 green bean galaxies to train a different model so that you can go and search for more green bean galaxies. It doesn't have to be green bean galaxies, just a rare object. This is probably one scientific use case for a model like this. Yeah.
Right. Or you feed it millions of galaxies and it's properly drawing nice galaxies, and then it draws a superstar destroyer, and you're like, wait a minute, we should maybe image that galaxy, see what's up with that. Is that a Dyson sphere? Is that is that a galaxy far away? That's really interesting. So once you sort of start to see the capability of the potential of this, I mean, it really sounds to me like we don't even know what's possible. And so now you just look for data to consume. And so is there a lot of unused data out there, do you think?
For astronomy, definitely, which is one of the reasons we've been doing this multimodal universe project, is so that we can get this data nicely packaged so people can easily take it and use it. At the moment, it's there's different groups releasing data all openly, which is very nice, but it's more difficult to access if you're not an astronomer and you don't know exactly how to go and get it. But this multimodal universe project is going to be on Hugging Face, so you can just go on there and access it. So that's one of the things I'd like to do as well, is to democratize access to astronomy data, because I think it'd be a very nice thing to do, and it would be a beneficial both for astronomy and for machine learning research. So I think it's a very good source of multimodal data that maybe isn't out there yet in a similar format.
And so what work needs to be done to put this into a situation that maybe scientists could get access to it?
So I suppose astronomers have access to it already, but if you don't have astronomy training, you don't know exactly how to use and process this data. So I think maybe a lot of documentation needs to be done, just packaging it up nicely, that kind of thing.
Well, yeah, but let's say that I'm an astronomer. I've been working on, I don't know, I write Python scripts. I've been accessing Gaia data and pulling down, tens of thousands of white dwarf observations, and I'm looking for some kind of, needle in a haystack to try and sort of do some scientific study on. And let's say I wanted to say, well, what if I fed all that into AstroPT and then look for some kind of, where would I go to actually start to do this work if I wanted to try and play around with these models?
So I suppose the first step would be going to there's an open GitHub. The code is all open source. It's ready to go. You can go there. You can download the GitHub code, feed in your data set, and it should just work. There's also a Discord server as well, where we're all chatting on there about AstroPT and large observation models and other deep learning for astronomy stuff. So yeah,
we'll put some links to that all in the show notes.
Yeah.
So then, would I be like fine tuning on existing data, or would I be training on just my 70,000 white dwarf observations and nothing else in the system, or would I be looking to fine tune an existing data set?
So ideally, I'd like to get to the point where you just take the AstroPT model and you fine tune it on your specific data set, just so it learns a little bit more astro knowledge on your specifics, kind of like you would do with a llama model. Right now, it's only been trained on galaxy observations, but the next step is going to be multimodal training. So we're going to have a model that knows of other astro modalities that you can then take and fine tune on your specific data set.
Right.
So that's in the works, but it's not quite there yet. So right now, you'd be training from scratch probably on your data set.
Right. And so when you say multimodality, you're not thinking, oh, I want text and pictures. You're like, I want spectroscopic data. I want X-ray observations. I want neutrino observations, gravitational wave observations, and just keep feeding that data in until interesting insights start to pop out as you query the
That's
data
exactly it. Yeah, just feed in all the data. It learns the physics, and then at the end of it, you have this nice model that knows all of this astro knowledge that you can then extract with linear probes or whatever you want to do. Yeah, that's the dream. That's where I'd like to get to, which is why this
Yeah,
is
yeah.
an open source project where like everyone join, we can train this model together with data that you might have.
And there's a lot of interesting work. Like the SETI researchers have been able to get a pipeline from radio observations to be able to pull data that is interesting to them to be able to search through for any evidence of a technological signature in the radio observations. Is getting data from these instruments and observatories, is that difficult right now, or is it relatively straightforward to kind of to take it all and feed it in? I mean, we're seeing all kinds of legal issues over in the regular world as the machine learning companies are having to face copyright issues and so on. Is it a lot simpler in the scientific realm?
I would say it's simpler, yeah, because you're not you don't have the problem of like copyright infringement or other things you might do in the textual realm. So it's nicer in that regard. Um, yeah, I would say it's a much nicer playground for developing these large models. You don't have to uh, like there's less ethical questions in my head when I'm using these models. So that's what I like about them. You can just use astronomy like it's all good.
So in your perfect world, there will
Hmm.
be pipelines of data coming from all of the telescopes, all of the rovers, all of the, I don't know, everything, all the gravitational wave observatories. It's all just being uploaded into this model, and then you are running some kind of training, kind of like how ChatGPT happens on a regular basis. Do you see it like some kind of continual process, or like, okay, now we're training version 3 with all the data up to this point?
I think realistically, it's probably going to be a version by version thing. I don't think it'll be continual just yet
Yeah.
because we're a small group at University BD. But it would be nice to get some continual pre-training going as well, where you could. There's a lot of cool research on about this about continual pre-training in the language world. So it'd be nice to be able to do something like this for these large observation models, these large transformers that feed in astronomy. If we can do this, we could also have a base model. You take it, you do some continual pre-training on it on your data set that you might have, your Astro data set, and then I can imagine you pushing it back to the base model repository or wherever we host the model. You can be like, oh, we've added this extra data set, we push it back, and it's a nice way to collaborate and like improve the model continually. So that would be very cool to do. I think, yeah, yeah.
Yeah, yeah. And so, one of the really interesting things that's happened with large language models is various kinds of emergent behavior where
Hmm.
you train it enough times and it starts to develop a theory of mind that it can sort of, put itself in the mind of another person to think what they're thinking. Are you seeing any glimmers of any kind of emergent behavior in understanding underlying physics and astronomy?
Yes, and this is one of the cool things I that was in the paper. So we have, like I said before, we have these linear probes that take the embedding space, they project it onto some scientific problem, and we found that certain galaxy morphology classifications emerge at a certain number of parameters. So I think it was uh, I think it was like 13 million parameters. You start seeing these questions starting being answered by the network. So if we can continue pushing this, it'd be interesting to see what questions it can't ask and at what point they start being answered by the model, and if there's some sort of correlation there. We only tested it on maybe 2 dozen questions, but if we can get a load of these, maybe there's a correlation between more difficult questions and easier questions. It suddenly emerges knowledge about the more difficult questions in a
So give me an example of a
predictable way.
question.
Hmm.
Like when you say a question, I mean, if it's just a bunch of pictures, can it only respond in pictures? Can it only respond in spectroscopic data?
It
So give me an
yeah.
example of how you might ask a question and how it might give you the answer to the question.
So we have some questions about the galaxy morphology. These are from the Galaxy Zoo project. So this is a citizen science project where citizen scientists, they look at lots of galaxies and they answer questions about it, like this galaxy has so many spiral arms, or this is heavily barred, or this has an artifact in it which is like a strange occurrence in the galaxy. And we take these questions, we encode the answers as a float value between 0 and 1, depending on how strong the answer is from the Galaxy Zoo citizen scientists. And we ask the model, the linear probe model, to answer these questions. So you can imagine the linear probe is taking the galaxy as an input, and then it's trying to predict how likely it is to be heavily barred, or how likely it is to have n spiral arms, or how likely it is to have a certain redshift, or have a certain color, or a certain magnitude. And these are the questions we ask it. We're not asking it like text and it answers in text. We ask it like a supervised question, like in classical machine learning.
Right. But essentially you're saying what is the likelihood that a galaxy is going to have a thick bar? And then it's going to give you a distribution between 0 and 1 that is telling you how often this kind of thing happens. And it has just discovered this through just ingesting an enormous amount of the underlying data.
Yeah, that's the case. So it's like what's the likelihood that this specific galaxy has a bar, and then it comes out as like, this is maybe 0.5 likelihood to be heavily barred, or this is 0.8 likelihood to be heavily barred, and we compare that to our answers that we already have, and then we know if it's telling us the right answer because we're comparing it there. And yeah, this is just an emergent property of us feeding it and asking it to tell us the next token in the series of tokens, which is very cool. It's not trained on this at all. We're just asking it after the training, after the pre-training, like, do you know this physics about the galaxy? So it's very cool that it picks it up just from this pre-training task.
And we are just around the corner from just enormous amounts of data coming onto the internet with the Vera Rubin Observatory. I mean, it's going to be putting out petabytes of data on a regular basis. Is that enough data? Is that too much data? I mean, how would you feed that kind of quantity into some kind of transformer model?
It's a lot of data. So you need a lot of infrastructures to do this. And that also means you might need a lot of money to do this, which it's difficult to get right now. But like, it's definitely doable, and more data is always good data. If you have the resources to throw it into the model, it's better to have more data. And yeah, so that's the reason. That's kind of the thinking behind these models. Like, we have all of this data. What are we going to do with it? Because we can't go through it manually. We can't really use supervised machine learning either, because it's difficult to find all the labels. So we need a very flexible, self-supervised framework like the transformer model, autoregressive transformer model, to process this data without us having to do too much manually. So if we have petabytes of data, we can just feed it in, and then physics pops out the other end after we do some fine tuning.
Sure. I'm sure that's exactly how it'll play out.
We'll see.
Boom, new physics.
It'd be amazing.
Right out the other side.
Mm-hmm.
Yeah. But that is the dream, right?
Yeah.
Like the dream is that, as with, say, the Earth PT that you were talking about, that you're just giving it pictures of Earth weather, and then you're getting predictions of future weather. That's useful for being able to predict what the weather is going to look like in a couple of days, with the same level of accuracy as all of this hard work of people doing all of these really complicated supercomputer simulations of all of the various factors. So what do you hope? Like, let's say it's been 10 years down the road. You've got an amazing pipeline of all of this data coming together. All of the big tech companies are gladly donating compute time so that you can keep training the model on it. What kinds of science do you think will be popping out the other end?
So I suppose the answer is the cool thing about these self-supervised models is we can train them and then find out things we didn't know to even look for, the unknown unknowns. So that's the thing I would find most exciting. If we can train these in such a way that we can do science to find things we haven't even thought of yet at the training time, that's what I would think is really cool. just to have a big general model that people can then take and run experiments on and find scientific answers that I haven't thought of personally, or the maintainers of these large models haven't thought of.
I mean, I know a lot of people have tried to do this using, say, things like OpenAI, where they've said, you've ingested every single technical paper that's ever been written on biology. Are there any connections between papers that maybe nobody's ever thought of? And I haven't heard of anybody coming up with anything ever that has been able to make any kind of insights. It makes what sounds like insights, but they're not insights.
Mm-hmm.
When someone who's knowledgeable goes, no, that's, we knew about that thing over there. That's nothing. So, and when you think about, like, there's been really interesting drug discovery that's being done. There's been really interesting material science that's being done, but it requires going forward where you say, where the model says, okay, I've ingested all of the chemistry that's ever been done, all the chemical compounds, and I understand their various behaviors. This is an area that could yield results, but you're only going to find out if you then create those compounds and then measure the results and feed those back into the model. Or same thing with material science, where you're actually having to take all these different atoms and mash them together and create things. And I wonder if you're not going to be able to get anything you don't already know, but maybe you'll get new questions. Do you know what I mean?
I think I know. Yeah, I think what maybe, correct me if I'm wrong, but maybe the question is, like, do we need a human in the loop here? And I think definitely to ask the questions to the model to process the data that they have, and then think of ways to get the answers from the embedding space right now. That's something
Yeah.
that we need, and this is where the creativity comes in that maybe isn't there right now with the language models when you're just asking it to do biology research as a language model.
Yeah, I mean, the emergent data that hasn't, the emergent behavior that I'm waiting to see is insight,
Mm-hmm.
and that hasn't shown up yet. I'm waiting for an LLM to say, by the way, I noticed that these people over here found this interesting protein, and those people over there found this interesting behavior. And if you just put two and two together, you'll actually come up with there's a hypothesis here. Maybe someone should go and check this out.
Mm-hmm.
And I think in terms of, and then back in terms of astronomy, you think about it, that it's going to look at 1 billion galaxies, and then it's going to notice 3 that are weird and say, I found 3 weird galaxies because they look this way, but then the spectroscopic data over there looks different. Maybe someone should
Mm-hmm.
take a look at this. And I think that's the hope, right? The hope is that the system is popping out uh, mysteries that then a human can go, okay, yeah, let's try and figure out what's going on here. And do you think, as opposed to just more of what we know, and
Mm-hmm.
that's what I'm seeing so far with large language models, and I wonder if that's the same for science, and how do we get around that?
I can think of a way we can find strange objects with the model we have right now. So you could take the embeddings, like I was saying before. We in the paper we train them to answer some scientific questions. But if you take them and then you have the embedding space, you can imagine this as a high dimensional space of every galaxy it's being fed, or every spectra is being fed, or whatever. The ones that are far away from every other galaxy are going to be strange, because the model's like, what are these? I'm going to put them over here in the embedding space because they're strange little objects. So then you could ask the model, where are the end galaxies that are far away from the bulk of the data? And you can do this with a cosine distance or something like this. And then it shows you the galaxies in the data set. And you're like, oh, okay, these are strange. Like, maybe this is some new science popping out here. So that's maybe what we could do to find some new interesting objects, or some strange science that isn't normally there, that isn't in the current literature. So yeah, I think it's certainly doable here. I can't think of an analogy for that for large language models, because obviously, well, maybe textual embeddings, if you have an exciting paper or something that's very out there, but it's like something cool that's sort of related to some other papers you're looking at, you could get recommendations in this way. So you could think of that as like the textual side of the same question.
Yeah, I mean, the dream is that you feed it everything that's known to humanity, and then obviously you ask it, what's the meaning for life, the universe, and everything. But
Hmm.
apart from that, you might say, we've got this problem of the Hubble tension. Have you got any insights? And the hope would be it would go, oh, sure. Isn't it weird that galaxies are somehow moving away from each other at this redshift, but not at that redshift? Maybe you should look there. And
That's the dream. Yeah.
yeah,
Yeah. And I'm hoping eventually we can move towards this. Right now, we, to do this, we would need the models to have knowledge of text, so you could it would know about Hubble tension in the literature, in the astro literature, plus galaxies, plus spectra, plus anything else it might need to answer this question. But you could think of it as the AstroPT being a giant RAG thing for the textual model to then look in this database and do some experiments in there. Maybe be like, oh yeah, these galaxies are doing uh, something uh, predicted by the Hubble papers or whatever. But yeah, I can see it working. You just need to build every every modality into the model as possible, so it has the tools to answer these questions.
so that's a modality that you haven't incorporated yet, which is text,
Hmm.
right? You're not feeding it all of archive.
No, not right now. There are some colleagues in University TBD that are working on fine tuning language models on Astro archive papers. This is the Astro Llama series of projects. So there are people working on this, but I wanted to start clean, start with simply, so that then we can build it up to eventually incorporate text. But right now, it's yeah.
Do you think that would be useful or distracting to the model?
I would hope it would be useful because data is data, right? So if it has uh, a textual description of a galaxy plus the image of the galaxy, it should learn something correlating between them, especially if it has the rest of the paper describing this galaxy and oh, it's interesting because of this, and this.
Yeah.
Here's the data for the galaxy as well. I think it would be very cool to try this, and it'd be very
Yeah.
useful for the model as well and for answering these questions like you were saying.
I mean, it's interesting, say, with the latest version of ChatGPT, the O model, it's natively multimodal. So instead of it
Mm-hmm.
having to listen to your text, translate it into text, perform some kind of function on it, turn it back, it's able to just listen to the words that you say and then act on them and then speak in generate text or generate words. And I wonder if having that just be natively understanding the text of that the papers were written on, being able to could it then start trying to write papers? But my guess is it would just be hallucinatory nonsense.
I think until the model passes a certain threshold of billions of
Yeah.
parameters, maybe we shouldn't let it write papers.
We should
uh,
absolutely not let it write papers.
yeah,
Yeah.
but I don't.
That's
Yeah,
already a problem in the scientific field, is
yeah,
people using OpenAI to write papers.
yeah.
Yeah.
But yeah, I think. I think it's an interesting question for sure. I would like to try. I think I would like to have everyone vet it very, very thoroughly before we start relying on it and not vetting its findings. Because then you start down a dangerous path of science done purely by machines with no one looking at them. It'd be a very strange world to to go down that route.
So when you think about the kind of data that you're getting right now, what would be like the perfect data if you could feed it in to start answering some of these interesting questions, do you think?
I
That
think
maybe
the
doesn't
per
exist
yeah.
right now.
I don't think it exists right now. I think the perfect data set would be inline observational data alongside the archive papers, alongside everything you can throw at it in a format so you could feed it in interlaced so that the model would learn just from predicting the next item in the sequence uh, something central about the scientific process. I think that would be amazing to do.
Give me an idea of how that might work.
So you could imagine each token being a multimodal text or galaxy observation or spectra or a time series, feed it all in, and in predicting the next like token or of text or galaxy, it needs to learn something about the underlying science, because otherwise it wouldn't be very good at predicting it. And if it's perfect at predicting it, it's going to be better at scientific analysis than a model that's very bad at predicting this interlaced paper multimodal like data set that we're talking about.
So would you do that with pre-training? Like, would you take your data, have a really smart but not necessarily great at astronomy LLM, prepare the data in a format that then some astronomy related one could then feed on that data to have it all nicely in the same structure?
It'd be nice. I imagine it would be, yeah, it'd be very nice to be able to do this. I think that's a good route to go down. But first, we need to build in the textual domain into these models. But yeah,
Yeah,
in a
I mean,
perfect world, yeah, yeah.
it's been really interesting. Like Microsoft released their Phi model,
Hmm.
and it's surprisingly good for how small of a model that it is. And the answer appeared to be obsessing about the quality of the data. That you
Yeah.
don't just feed it all of Reddit, you don't just feed it all of Twitter. In fact, you have to go through line by line, sentence by sentence, and make sure that you've got good stuff before you actually, because it's garbage in, garbage out. But the question that I was asking was more like, if there was a data set, like you're having to scavenge from Gaia, from Desi, from Webb, from and shortly from Vera Rubin. But if there was like the kind of data that would be really useful to learn from, could you sort of imagine a perfect data set, and then then we'll figure out how to get that data? What would be the ideal data?
So I would say the ideal data to train the model would be something that has a very high signal to noise ratio. So it's got a lot of important physics in the data and not a lot of craft. So not a lot of like blank space or noise or whatever. So that would be the perfect data set to feed this. And I think we have so much data coming in astronomy, we could do some pretty aggressive cuts to get this good high quality data if we had some people looking at this. And I think that's what I did with Phi as well. They cut it aggressively, or no, I think they actually took synthetic data from GP from some large language model and trained the Phi model on this. I don't think we can do this in our case, but we have all of this data, this raw data from these telescopes that we can then cut, and we have high signal, low noise, and it would be much better for the model to train on this, so it's not learning things that aren't particularly relevant for the physics. Yeah.
Right. So you're going like 3 steps forward, 1 step back with high noise. It'd be better to just go 3 steps forward and no steps back with
Yeah,
low noise.
that's
And
exactly it. Yeah.
and are there good? And I guess I mean the problem is always all telescopes are going to be trying to observe at the very edge of what they are capable of observing, and so you're always going to just like at a certain point the noise makes the images unusable, and so you're
Hmm.
always hitting high noise
Yeah.
because you're trying to eke out the most possible science from your data.
So I guess if it's new, like a new type of galaxy or the edge of our observable universe, and it's high, still high, like telescopic noise, I would argue that there's more information in that new galaxy compared to another, uh, just another spiral galaxy. So high signal to noise, but maybe not telescopic noise, just like important information or useful information compared to
Yeah,
just blank space. Yeah.
no, it's interesting. Um, Michael, what are you obsessed with right now?
Right now, I'm obsessed with, I guess, scaling these models. Yeah, I want to see exactly how far we can push them, how big we can make them before hitting a barrier. So we hit a barrier with the Galaxy model at 90 million parameters, but I think we can push way past this if we improve the signal to noise ratio here. So that's what I'm obsessed with. I'm trying to figure out a nice way to scale these models as far as we can push them and see if we can build something as as big as these large language models. I think that'd be very cool. Exactly how far can we push the transformer architecture just to get this rolling? Yeah.
And I mean, 93 million parameters is so small compared to
Exactly. Yeah.
these monster text ones and image ones that are out there. And so what's missing then? More compute, or just more people helping to get the data ready and prepare it for the, what did you call it? Was it AstroPT? What is the raw material called? The pile, the
The
version of the pile.
so that's multimodal universe. That's the
Okay.
the big data set that we've been
So
building.
do you need compute, or do you need more contributors to the multimodal universe?
I would say probably both. So we need compute, we need
Yeah.
more contributors to the multimodal universe, more contributors to large observation models for astronomy like AstroPT. Just more in general, and I think it would be very exciting if we can build something together for science, just so that we can get this working. It'd be very cool to do, and all
Yeah.
of this stuff is out in the open, so anyone can join. It's not like restrictive or anything. You can just go and join, ask some questions on the Discord, join the GitHub repo, and do some pushes. Yeah, yeah. So
And
that's the dream for me.
like, I have a lot of people who listen to what I do, and they are in the computer field. They're they're working in machine learning, or they're working in various stuff, and they love astronomy and they'd love to contribute. So what would be the best way that people who are listening to this interview, and they're really okay, yeah, they want to try and put all of that technology knowledge to science?
Mhm.
What is the best way that they can get involved?
So they can join the Universe TBD Discord, which I can give you the link for this, and it's a Discord server that's open to all, like Eleuthera AI is, and we're trying to develop uh, astronomy, like machine learning models, not just AstroPT. We've also trying to develop Mamba models on there for astronomy, plus large language models that are trained on astro, like archive papers and astro knowledge. So I think the best thing to do would be just join that Discord, play around a bit with our projects, what's going on, like uh, have a look at our codes, because we're astronomers, we're not machine learning scientists, so our code is probably not not the best
Right. So this
format,
is the
but like,
thing, right? There's all these
so it'd
machine
be
learning
perfect. Yeah,
astronomy fans who can't wait to get involved in a project, and this sounds like a great project to get involved in. Well, Michael, good
yeah.
luck on unleashing this technology to come up with new theories about the universe. I look forward to the new discoveries.
Thank you. It was great talking.
I hope you enjoyed that interview with Dr. Michael Smith. Now, I'm going to give you some more thoughts and feedback, but first, I'd like to thank our patrons. Thanks to Abe Kingston, Adam Schaefer, Andrew M. Gross, David Giltonen, David Matz, Dennis Alberti, Dustin Cable, Jeremy Mattern, Jim Burke, Jordan Young, Josh Schultz, Modzo, Paul Rohrbach, Stephen Krasaki, Stephen Fowler Munley, and Vlad Chipolin, who support us at the Master of the Universe level, and all of our other supporters on Patreon. I've been waiting for something like this to come along, which is that, there's so much data. I talk about this all the time, that you've got the Virurum Observatory that's going to be generating petabytes of data dumped directly onto the internet. All of this data coming from Gaia, all of this information coming from Euclid, from DESI. Like, there's too much data. And yet there are all of these mysteries, these questions that we have. What is dark matter? What is dark energy? Why is there more matter than antimatter in the universe? How did the first galaxies form? All of these questions. Data meet questions. And hopefully, finally, we're going to have some form of tool, some kind of machine learning system that can actually help us make sense from all of this data that's being gathered by all these new observatories. And this sounds like the right direction to me. And so I don't know if you got the gist in the conversation, but Michael is definitely looking for more people to get involved in the project, especially the kinds of people who have technical knowledge, programming experience, machine learning, that kind of thing. And if that's you, and you've always wanted to get involved in an astronomy project, this is your chance. So I'm going to put a link to the AstroPT paper in the show notes. I'm also going to put a link to that Discord chat that Michael was mentioning, so that you can go and join, say hi, and see how you can help out. And maybe we can have a computer help us solve some of the biggest problems in the universe. All right, we'll see you next time.